To see a few new faces in the audience tonight. I hope you enjoy the evening as we've got a great couple of talks lined up. Just for people that are new, the order of events is generally first speaker comes on, 20 to 30 minutes chat. Anyway, without further ado, I'd like to introduce you to our first speaker, Jason Cheung, who's going to talk about quantum chaos. Thanks, Jason.
Thank you, Simon. Just morning. Okay. Hello, good evening. So I'll just start with a very quick slide just to introduce myself. I've only started coming to these events about 4 or 5 months ago, but I've known about it for a number of years through Jim Manning, who I can't see here. I've actually worked in IT and for various reasons just gravitated towards Reading, and I've been here for 17 years. Last 12 years I've really been working on UK rail software in all of that, but I've worked on planes and cars as well, so quite a lot in transportation. My current job at the moment is service delivery manager to what's a journey planning bit of software. So this is for UK Rail again, so we take the train timetables, train fares, the complex rules that you have in how you apply those rules and journeys and all that sort of stuff, and wrap that all in an optimization engine to find the fastest journey from A to B or the cheapest journey from C to D. So that bit of software is actually under the hood for National Rail Inquiries and Trainline. So if you use their software or their websites or their apps, it's actually passing that request through to this little journey planner that we have under the hood. So that is me on a slide. If you want to talk to me on any of that, then feel free to grab me upstairs over a beer or two. But what I'm here to talk to you about is something called quantum chaos. This is something I studied before I started working, so I actually did a PhD in it. So this is going back 17 years or so. I found it quite interesting then, and I thought I'd give you a bit of an intro to all of that, really. I won't actually go into the details of my research. I mean, my title of it is Resummation and Correlations of Zeta Functions. It's a bit of a mouthful. I say I'm not going to go into the detail, but what I wanted to do is give you an overview of the field that it was in, which is quantum chaos. So what is that? Okay, so I'm going to break my talk presentation into 3 parts. One is to kind of explain what quantum chaos is all about. And that kind of falls in 2 parts. One is about chaos, one about quantum mechanics. The final part of it is how you can actually use this to win $1 million. So, yay! I'm not saying it's going to be easy, but that is a fact. So, I just want to start with chaos. A lot of people will be familiar with what's called the butterfly effect. It's a popularized term where a butterfly flaps its wings and you end up with a hurricane in a different continent. What I want to do is try and add a bit more bones to that, so you understand what a more technical definition of what chaos is all about is what I'd want to start with doing. So in order to kind of explain what chaos is all about, it's probably better if I start with what is not a chaotic system, what's called a deterministic system. And the simplest system that I can use to demonstrate this is called a billiard system, where you have a rectangle and you have a ball just bouncing around it. It's fairly predictable behavior. You just apply fairly simple geometry, maths and physics, and you can accurately determine where that ball or particle is going to bounce around on that rectangle. And you see this with snooker players all the time. You know, they're able to play trick shots around the table and all that sort of good stuff. So that's a fairly simple system that's called deterministic. But by changing the shape of that rectangle, you get something quite interesting. And what you can do is if you add semicircles to the ends of that rectangle, you end up what's called a stadium billiard, for kind of obvious reasons. This is an example of a chaotic system. By that, I mean, if you set a ball off in one direction and you try to repeat that, but there's a slight difference in that initial angle, that difference will magnify over time as it bounces around that boundary, that shape. And there's some I pulled off the web, and you can it kind of illustrates how these paths diverge over time. Okay, so I guess the point to take from this is that if you were to challenge a top-notch snooker player to try to play the same shot twice on a stadium, billiard, or any kind of chaotic shape, they won't be able to do it. The laws of physics will beat them on it. Everyone with me so far on that kind of definition of it? So this is the definition I want to use rather than the butterfly effect, which is exponential sensitivity to initial conditions. It's just the definition that we used when we were studying this back in the day, and it's still quite used throughout this branch of mathematics. So any slight change or error in the initial conditions just gets magnified quickly over time. And this, what I've done here is, again, something else I pulled off the web, that if you let that ball bounce around for a long time, you'll see very complex structures developing. Again, this is, when you look at that, you kind of immediately think that's chaotic. Okay? So I think that's chaos in a nutshell. Everyone kind of happy with that sort of very simplistic definition? I realise I'm kind of rushing through some of the slides here at the moment, so I'll try and pace myself a little bit more. So moving on to quantum mechanics. So this is, again, something I can't really do justice to in the time I've got. It's a massive field of study, of course. But what I want to do is just run through a couple of bullet points as to what quantum mechanics is all about, some of the features of that, and some of it I'll come back to some of that to tie this all together, really. So firstly, it's where, I put it in a bullet point, strange things seem to happen in that it doesn't behave in the way you would expect in the real world. Okay, that's what quantum mechanics is all about, it's just strange things happen. So you get, one of the first things that's worth mentioning, and a very good characteristic of a quantum system, is that you get discrete energy levels. And the best way of thinking about that is irregular rungs on a ladder. So a quantum system can sit here or here or here, but you can't sit in the middle. It doesn't allow you to do that. That's what quantum mechanics is all about. This is not like the real world where you get a continuum of numbers or time or speed where you can measure things down to almost an infinite degree of precision. You can't get it in quantum mechanics. So that's kind of one difference between the quantum world and the physical world. Okay. There's strange things called duality, where a quantum system exhibits behavior of a particle and also a wave at the same time. It's very hard for me to describe in a short space of time, but it's just one of these strange things that happens in the quantum world. It also gives rise to a couple of interesting problems which you may have heard of. Probably one more famous is Schrodinger's cat paradox, where you put a cat in a box with a canister of poison that's attached to a radiation detector, and there's an atomic particle in there that can or cannot emit a bit of radiation. And the thought experiment there is that if the box is closed, the cat is both alive and dead at the same time, because the particle has this radioactive particle has emitted radiation, and it also hasn't emitted radiation at the same time. And it's only when you open the box that it collapses into one of the states, whether the cat's alive or dead. It's a very it's it's an odd sort of experiment to think about, but it's a natural conclusion when you look at what quantum mechanics sort of means. And the last thing I want to mention is something called the Heisenberg uncertainty principle, which means that in a quantum system, you can either measure the direction a particle is moving, or you can measure its speed. You can't measure both at the same time. And that's, again, another facet of quantum mechanics. And Heisenberg was popularized in Breaking Bad by the pseudonym adopted by Walter White, of course. Okay? So that's, again, is... So again, that's kind of quantum mechanics on a slide. I don't know if there's any quantum physicists in the audience here who feels offended by this very brief overview on that. But if you've got any questions, then shout out. Okay. Right. So onto what I was actually studying, which is, again, the subject of this title is quantum chaos, and it ties both chaotic behavior and quantum mechanics. So there's always been a body of work looking at quantum mechanics and how that relates to the real world. Quantum chaos was specialized in looking at how these chaotic systems, these classically chaotic systems, behave and what their equivalent forms of that are in the quantum world. Okay, and the definition of it really is we're trying to understand relations between quantum mechanics and the classical, the classically chaotic system counterparts in all of that. To go back to the billiard systems that I mentioned earlier, those chaotic billiard systems are a way of analysing and studying this branch of mathematics and physics. And one way of thinking about it is that if you've got this billiard system that I showed earlier of this ball bouncing around in a stadium shape, so that's a classical system, which is, again, chaotic. But in the quantum equivalent of that, the way to think about it is that it's a drum. And what you then get is a stadium shape, but you have a membrane, and you can that oscillates, and that will. And as with any kind of oscillations, you get natural frequencies. Those natural frequencies can be thought of in some ways as these quantum energy levels of the quantum system. Okay. There's been a huge body of work in looking at quantum chaos. There's lots of theories and lots of proofs about how the statistics of these quantum energy levels and how they relate to the classical system. Specifically, there's a number of functions you can look at that define the energy levels in terms of these quantum systems in terms of the underlying periodic orbits in the classical system. And this is something I forgot to mention earlier. That let me just go back a couple of slides. So in these classical systems, you get these chaotic trajectories in that, as I showed before, but there are also some trajectories, some patterns that are not chaotic. So, for example, a ball bouncing upwards and downwards or horizontally, they just repeat themselves, trace themselves. If you hit that precisely, that's what will happen. There's also another one where you bounce it around almost like a rectangle within that stadium shape. Those are periodic orbits in the classical system. So, am I going to, sorry about this. Where am I? Okay. Right. So, one thing that has been found in quantum chaos is that depending upon the symmetry of the classical system, so in that in that particular example of the stadium, it's got certain degrees of symmetry, and these chaotic systems, there are ways of categorizing those symmetries, and it turns out there are actually 3 groups of these, and they're called the Gaussian unitary ensemble, the Gaussian orthogonal ensemble, and the Gaussian symplectic ensemble. The point here is that with these classically chaotic systems, depending on the symmetry, and you look at the statistics of the corresponding chaotic system, the statistics of the energy levels of the corresponding quantum system, it will fall into one of these 3 categories. It's it's interesting in a number of ways. Just to illustrate this, so this is a statistic from what's called the first of those that I mentioned, the Gaussian unitary ensemble, and this particular graph is of what's called the pair correlation statistic. As I said earlier, in the quantum world, you get these energy levels that sit at certain levels on this, which again you can think of as these rungs on a ladder. The pair correlation statistic is looking at the distances between neighbouring rungs or these energy levels. And if you get enough of them, what they found in the case of the Gaussian unitary ensemble is that they follow this curve. So the research I was doing 17 years ago was again looking at some of these statistics of these energy levels and how they relate to quantum systems, kind of looking at ways of refining some of the mathematical approximations that they could make to understand the correspondence between these systems and why they fit into these certain categories and all of that. Do you have a question? Any questions so far?
Yeah, I've got a question.
Yeah.
I can't see how that's... I mean, sine squared is going to be limited to 1. X squared is going to go to a large number. Oh, I see.
It's 1 minus. Yep. Okay.
So the idea is that time's progressing. Is it this what X?
No, X is the distance between these energy levels in the quantum world. Okay, so it's the I say so. That's the way I think about it. One way to think about it is that there's a natural at this sort of level here. There are no you won't find any energy levels that are on top of each other because they always have these discrete energy levels. So it's always going to be 0 here, and then there's this tendency for these energy levels to repel each other. Everything here has been normalized, of course. So you take these energy levels, you look at the pair correlation, and you have to normalize it in certain ways to get it to fit this. But if you apply the same normalization on any of these chaotic systems with the same sort of symmetry, that's the pattern they fall into. Okay. Right. So, kind of onto the last section of my talk, which is really about which might seem a little bit left field, but it's about number theory. What I want to show here is something called an Euler product. Again, it's fairly, it's a bit of mathematical algebra for you guys. So it's a series of studies since for a couple of decades, so certainly in the 18th century or so. It's been looked at and it's been analysed quite a lot in many ways. And it's interesting in a number of ways in that what you have is an infinite sum of the natural numbers. So these are the counting numbers 1, 2, 3, 4, and all the way up to infinity, multiplied by x. Again, it's just x is any value. It's just a function of x. And you can write out long form in that sort of form. But what is interesting about this is that you can also write it as an Euler product, which is a product over prime numbers. And you can expand that product, and you will, again, it's fairly standard algebra to be able to expand and prove that is the case. But it's interesting in that it's one of the simplest relationships that you can define with natural numbers and prime numbers. And we all know that the importance of prime numbers plays in modern day within encryption and it's quite, and just generally in pure mathematics of prime numbers. Okay. So this is the important thing here is that this is a function considering where x is a normal value. You can take 1, 1.2, 1.3. Natural numbers is any kind of value you want. A German mathematician started looking at this in terms of what happens if, instead of looking at these counting numbers, you think of x as a complex number. And for those of you who don't know about complex numbers and stuff, again, the simplest way of thinking about this is you have a line of real numbers. You have 0 in the middle. You have 1, 2, 3, 5, 10, infinity shooting off over that way, and over this side you get -1, -2, -3, minus infinity to the other side. So any real number, any natural number that you can see in the real world will sit on this line, in this horizontal line. Imaginary numbers are, again, is something you can't, are just that, they are imaginary, and it corresponds to the square root of -1. Some of you may have come across this in A-level mathematics and so on. And how that maps out on this horizontal line I've just visualized in front of you is that the imaginary numbers, which are, let's say, square root of -1, then expand vertically. So you get 0 here still, you get square root of -1, which is I, square root of -2, two lots of square root of -1, 2i, 3i, up to infinity I, stretching upwards, and then you get -i, -2i, -5i, stretching downwards. So you end up with a coordinate system almost of real numbers this way, imaginary numbers on the vertical axis. And so that's complex numbers again in a couple of slides. So this is the function that Riemann looked at, and it's called the Riemann-Zeta function, where z is a complex variable now. And this particular function, again, because of that previous definition with the Euler product that's shown earlier, appears quite a lot in natural mathematics and physics and pretty much everywhere. It's quite an important function. And one of the things that has been of interest and a big source of study is what are the zeros of this function. Okay. Yeah. Sorry?
I don't understand what that function, what does it say?
So that's the function I had earlier, except instead of being a real variable x, it's a complex function, and that's just a shorthand way of expressing it. It's okay. It's a kind of like you'd be familiar with sine x, for example. Yeah. So sine is just a way of saying here's a function of sine. Oh, that first symbol is the Greek zeta letter. Okay. So so this is the Riemann hypothesis that dates back to the 1850s, and Riemann believes that the non-trivial zeros of that function. Forget what this analyst can do. This is something I pulled off Wikipedia, but it's again just to be fairly precise on this, but you can ignore the analytic continuation of that. But it's the Riemann hypothesis is that all non-trivial zeros of the Riemann zeta function, that function shown earlier, all have a real part of half. So they all lie on this line of real part of half, and it's important because it has, again, just from here, it's far-reaching implications for number theory and the distribution of prime numbers and stuff. And the reason why this is also of note is that this was one of 7 problems set down by the Clay Institute of Mathematics in America in the year 2000 as these are the biggest problems that are unsolved in mathematics, and this is one of those 7, and each of those 7 problems has $1 million prize on its head, so anyone who proves this will get $1 million. So that's the $1 million challenge. So what does the Riemann hypothesis look like, I guess? So again, I kind of mapped out this coordinate system, real numbers across the horizontal axis, imaginary numbers across the top, and what's called this critical strip between 0 and 1. It's certainly been proven that the interesting zeros of it lie in this critical strip, but trying to narrow it down to prove that it lies in on that line a half is the big challenge. Certainly the general consensus is that it's true, but it's just one of those things that hasn't been proven yet. Lots of certainly people have also numerically found several billion zeros along this line, and they all have real part of half. But that's not to say that the 7 billionth and 1 lies off of that real line. So. Okay, so kind of to tie this back to where I started with the research in quantum chaos. If you look at those zeros that are on this line, so they've got these, they will appear on certain positions, all on here. If you look at those and again look at the statistics of how those are separated and everything else, what you do find is that the statistics also correspond to that Gaussian unitary ensemble I mentioned earlier. So that sine graph, that 1 minus sine graph that I showed earlier, the nearest, the separation between those zeros also fits that same pattern. And the general thought is that that's too much of a coincidence, really. There's a separate hypothesis, which is that behind this Riemann zeta function, there actually lies a quantum system whose energy levels correspond to these zeros of the zeta function, and the classical equivalent of that particular system is also a chaotic system. So it's pulling all of this stuff together. So that's kind of the end of my talk, and I kind of run through that fairly quickly. Any questions from anyone then? No?
So I guess what they're trying to find out is they're trying to prove that the actual solutions for that function, where it is the real part is a half or an Argand diagram. By proving that, what kind of implications does that actually have for?
It's one of the main implications of that is that if you were to, again, this all goes back to prime number theory. There's something called a counting function of prime. So as you go along from 0, every time you reach a prime number, you just add 1 to it. So it's a counting function of all the primes lower than a number x, for example. You can get a very, very good approximation of that. I can't quite remember what it is, but there's a very simple approximation that runs through all of that. But then you get all these oscillations around that, which create these steps as you're moving along for every single prime that you come across. That fluctuation and those steps are actually a function of that zeta function. Okay. What else can we say about that particular function? It's just something that appears quite a lot if you're doing any kind of analysis on numerical in mathematics, especially with prime numbers and stuff, because of, again, going back to that earlier definition of natural numbers and prime numbers. It's a very visible display that there is something there. Okay. Okay. Is that okay, Simon? Okay. Got any? Yep. Okay. Thank you.